So this is the second lesson for Chapter 3. In the first lesson we were looking at how to calculate work where the force was constant. Might have been at a strange angle, but at least it was a constant value. And for this one, we're not so worried about the angle of the force and the displacement, but we're going to be looking at issues where the force is actually changing in size. So this is part 2, and this is actually in your little booklet. So this is work with a force that varies with distance. I've just got a little graph here of a force that might be being applied to an object, and then on the across axis is actually where you are located in the room. Where's your displacement? And you can see that at different spots in the room, as you displace your way across to the right, the force value kind of modulates. It goes up and it peaks and comes back, plateaus for a while, and then drops down to 0 in the end. Well, our usual plan for finding work is to go force times distance. And I'm not, too worried about the angle here, but just what do you do when the force is actually changing in size? And the answer is, it's a bit of a little calculus deal. It turns out if you find the area underneath that graph, that force displacement graph, you'll be multiplying lengths and widths, and you'd have forces and displacements multiplied together. And so this area underneath is actually what you're looking for. And so somebody might say, well, how much work did I do from location A until I got to location B, right? Those two different displacements in the room. And you'd say, hang on, and you just shade it in with a pencil, and then you say, all right, I just have to go and find this area. And once you found the area, that is going to be the amount of work that there is. So, worth a little note in there. The shaded area represents the work done to move it from A to B. Okay, great. Well, how do you go and find those areas, right? What's the sort of strategy for accomplishing that? And I want to suggest to you that there are two methods that we're going to use for Physics 12 to do this. One method is to look at it, maybe like this picture here, and say, it's not all that complicated. It's just like a rectangle with a tiny little triangle sitting in the upper left corner. And if you can get at it with some simple shapes, then that can be a great way to go. Another option would be to use some calculus, and we're going to need to do that when we explore work done involving the force of gravity, when you've actually got a force that diminishes as you move away from the Earth. So we're going to do a little bit of both. We'll spend a couple of minutes here looking at some simple shapes, right, and how you can work with those, and then most of the day is going to be focused on gravity. To do a story where you involve some nice simple shapes, we're going to take a look at springs. And what I remember from Physics 11 is that the more that you stretch a spring, the extension, or this letter X, the more force that the spring pulls back. And obviously the more force you'd have to apply to keep going. And so if you do a graph of how much force is actually involved in the story to battle the spring as you stretch it out to an extension of X, so this isn't a length, but actually an extension, how much it grows, it's a nice linear graph that actually hits the origin. Okay, well, if we're going to try to do this work equals force times displacement, we know we're going to be looking at the area underneath this graph. And our strategy now is to say, all right, how can we get that area? Well, it's just a triangle, right? So it's not that bad. We can just go 1/2 the base, which is how much you've extended it, multiplied by the height, which is this current kind of peak force value when you've gone to an extension of X. All right, so I'm just definitely looking for the area of a triangle in there. Okay, well, just going with 1/2 base times height. I'd have, 1/2 my current extension value multiplied by whatever the force is right here, right at that spot. That would be my peak of my triangle. But I can actually calculate how big that force is just by using the equation, F equals kx. If you extend the spring by x, then currently the force that you're battling is kx, right? That would be the peak force value up here on the graph. And so if you desire to, and it's not necessary, but if you desire to, you can make this equation now that will say, hey, here's how much work it is to stretch that spring. Another way to word that is you could say, here's how much energy will be in the spring once you're finished stretching it. And so this potential energy of a spring, the work it takes to stretch it, is 1/2 k times the extension squared. And it is quadratic, right? So if you triple the extension, there's 9 times as much energy involved in the story. I'm just going to make a little note in here. This 1/2 kx squared is the work performed from stretching the spring from no stretch at all. It has to start here. That's the only way this formula is going to work well. out to some final stretch value of x, right? That'll be your displacement. I've managed to stretch at x. The key thing that we're going to look at for the next couple of examples is if you like this little equation here, 1/2 kx squared, you have to realize that that's with respect to nothing at all, no stretch at all. Okay, here's our first example of a couple. Let's say you have a spring that's 12 newtons per meter for its spring constant. That's how stiff it is. And we're going to try to figure out the work required to pull the spring from no stretch at all, okay, that's good news, all the way out to 5 meters. So the picture would look something like this. Okay, you're extending the spring until you get to a displacement of 5. We do know that the force as you go is 12 times however much you've extended it. So if you've extended it by 5, then 12 times 5 is 60. Your peak force value there would be 60. Okay, trying to find this work. I just want to suggest to you that there are two identical ways to find the answer. Some people latch onto one thought or the other. We're going to be finding the area underneath that graph. So you could say, you know what, I'm pretty comfortable calculating areas. Comfortable with that from my math classes, so I'm just going to go 1/2 base times height. A base displacement of 5 and a height force of 60, you're done. You have the right answer of 150 joules. Other people might say, well, hang on, a minute ago we just made this nice little equation that does this calculation for us in some ways, this 1/2 kx squared. It's a 1/2 times the spring constant of 12 and then the extension 5 squared. That also gives you the 150. No surprise, right? I mean, it's really just finding the area of that triangle. So two options there for finding that work or that potential energy that's now in the spring. But now it's going to get more interesting. You've already stretched it 5 meters, and the question is, how much work to pull it from 5 meters, another 3 meters out to 8 meters? Okay, so the picture now looks something kind of like this. We have to find the shaded area there from 5 all the way out to 8. And it's no longer just a nice innocent little triangle with its lower left point down at the origin. It's now some interesting trapezoid. As long as you find the area of that trapezoid, we're totally fine, right? And I want to suggest to you that there are a couple of options for doing that. One, as you can see here, is you can say, well, that's actually like a rectangle and then a little triangle sitting on top. And if you start to think about the numbers here, we know that that first vertical value is 60. And then if you go 12 times 8, this final force value is 96 up here. So this little triangle, it has a width of 3, and just comparing verticals here, a little growth there of 36. So one option is to say, hey, I'm just going to go area of a rectangle plus the little tiny triangle that sits on the top. And that absolutely gives you the right answer. 234 joules is what we're looking for here. Other people look at it and they say, well, wait a minute. Is there maybe a different way that we can go and get at this? Can we not find that green area by going with a big triangle and then subtracting off a little triangle of just white space in there? And sure you can. And there's even a couple of ways that you can do that. So on the top here, I'm just going with just my regular math, just 1/2 base times height. That's for the big triangle, minus 1/2 base times height for the little triangle of white space. And you get the 234. Other people might go, well, this is a perfect time to use 1/2 kx squared. We could go 1/2 the 12 times the 8 squared to do the big triangle, and then subtract 1/2 12 times the 5 squared for the little white space. Either way, you're going to get your 234. Moral of the story, if it's a nice shape that's made up of triangles and rectangles and trapezoids, it's not too bad to find some way to just wrestle out that area by hand. Or you can use that 1/2 kx squared if it works for you. But that's not really the main focus of the day. Probably the more important question is, how do you deal with stories that involve gravity? Because the force of gravity's got a real curve to it. It doesn't have a slanted line like Hooke's law for springs, but it's got this beautiful curve. So I'm just going to sketch things out. You've probably already got this in your little note template that goes with this lesson. Let's superimpose this graph of the force that's going to be required to lift a satellite up right on top of this little map of the world here. And so it's this inverse square law where it diminishes down very, very, very fast. And it really escalates quickly here as you get closer to the origin on this graph. We're going to be talking about going from here, the surface of the Earth, out to some spot where we might want to put something into orbit. We're going to try to figure out the work involved. So maybe from location A, one radius away from the origin of this graph, out to location B, some perfect little orbit location. And so our challenge is going to be to try to find that force times displacement. Now I'm going to swap out the displacement for an r, because in a minute we will talk about having something in orbit, and that distance we've gone out will actually be the radius of the orbit. So it's really common just to use r's here. That's why we used r's in the original force equation back in grade 11, was to get ready for Physics 12 with orbits. So our plan, same as a moment ago, we have to find the area underneath that graph. That will not be super easy to do because that graph has that curved top. And so at this point, you really have to trust some calculus in order to give you the right answer. And you might be thinking, this would be a perfectly fair thing for you to be thinking, that, oh, maybe the calculus, kind of like that 1/2 kx squared equation, maybe the calculus will find a way to find like this big area, and then we'll subtract off this small little white space area. It's a neat idea, but it turns out that doesn't actually work in that way. We have to be a little bit creative about how we do some subtracting in order to find that. But here's the result. We end up creating this equation with some calculus. There's no other way to create this equation. You can't just take the force equation and try to multiply by r and say, oh, look, it looks like that, and I don't know why the negative's there. The only way to get there is to use calculus. And so we have this negative gmm all divided by just an r. And we actually call this the potential energy in the story. Much like that work required to stretch the spring talks about how much potential energy is now in the spring when we're done. Okay, here's the deal with subtracting. If you were to think, like maybe I can do this all the way out to B and then subtract off the area out here to A, it turns out the area in this white space is infinitely large. And there's no way you can subtract these two infinities nicely. But what's really neat is the area from here out to forever, which is a really long way, is actually finite. It's not an infinite number. So you could actually calculate how much area there is to go all the way along this infinitely long curve, all the way out to forever, and it's not a big number because it gets so short so quickly. And so we will be doing some subtracting. But what's odd is we're going to be subtracting like this. We're going to find the area all the way out like that, and then we're going to subtract off the little white space of area that you don't want in here. And it's so strange to go all the way out to infinity like that, but the math is perfectly happy doing that. And so we're going to take it and run. We're going to see if we can get this to work. So the r's, when you do this deal, have to be measured to the Earth center. Right? So we'll always be taking our tape measure and starting from here when we measure. And the energies that you get are actually with respect to way out here. We're actually going to have zero energy when you're all the way out to infinity. Okay, so the reference point for the e's is r equals infinity. Now, in my classroom, you've noticed that there's a whole bunch of little silly stickers with little aliens up on the roof. That's just a little reminder to you for this lesson that this energy is actually with respect to, if you wish, the roof of space. So we're doing all of our measurements from the roof down. So where's the roof of space? I don't know. It must be way up there, right? There's probably aliens up there, right? And it's probably so far up that we don't see the aliens because, it's infinitely far up, right? So the aliens are just a little friendly joke saying, hey, don't forget that the energies are measured with respect to them sitting up on the roof of the classroom. But if we measure from the roof down, everything should work out great. Okay, let's work through this example here. We've got a 42 kilogram space probe. You're in charge of launching it, and it has to be located this far, oh, I don't like that word, above the Earth's surface. Generally, I like orbital radius, but this orbit, talking about how far it is above the Earth, we're going to have to fix that in order to get it to work. So if I'm not worried about changes in kinetic energy, if I'm just worried about lifting, then what I want to do is just find changes in potential energy. That should tell me nicely how much work it will be to lift it up. So if I can find the final potential energy using that new equation and then the initial and subtract, I should be good to go. So on your note package there, you can see that this part of your notes are split. We're going to talk about what happens when you use this equation initially and then what happens when you use it finally. So initially, your space probe is sitting there just sitting on the Earth, right? Sitting at NASA, they're working on it, getting it all ready to go. And later on, it's going to be way up in space, this far above the Earth. Okay, that'll be that gap space in there. All right, at the beginning, we're not going to say that it's at a height of 0. We're going to say that it's at a radius of 6.38 times 10 to the 6. We will always do our measuring for our R values compared to the Earth's center. So that's where we begin, is that far away. And when we go to do this calculation, we're going to just trust that calculus. So it's negative the G value for the universe, the two masses, and then we're going to divide by just an R, just a single R. Nothing gets squared in this energy equation. And when I tried that out, I found I had this massively negative number. That number is negative because it's telling you, hey, that satellite's not up on the roof yet. It's not up infinitely far from the Earth center. It's below that, right? And so this negative says you're this many joules below, and again, air quotes, the roof of space, right? The very top of space. Okay, well now let's go and check it out when we're in orbit, okay, when we're way up there. So now we've got this R value that goes from the center of the Earth all the way out to here. They told us how far it was above. Not super useful, so I have to add on the Earth's radius in order to find that whole little arrow you can see in there. And so when I do that, I get 7.8 times 10 to the 6. That's the number that we want to work with. Now, lots of times people will actually just give you the orbital radius. They'll say, hey, here it is, orbital radius. And if they give you that, great, take it and run. But if they tell you how far it is above or an altitude or a height, then you have to do that business there. Okay, recalculating. Let's find out how much energy we've got compared to the roof of space. You can see we're still not infinitely far from the Earth, so I'm expecting to see a negative number again. That's where this is going to come from. But it's not quite so deep down from the roof of space. We're a little closer as we work our way up. So I'm expecting a number that's negative, but maybe not as big in terms of how negative it is. And sure enough, it's negative 2.15. So those two numbers, I'm just going to go back a page here. Those two numbers tell you about how much energy you are short of being way up here, and that's why they're negative. So you have that negative 2.63, like way down below the aliens, and the negative 2.15, below but not quite as far. Okay, so we'll just use these little aliens as a silly little joke, a little reminder of how we're measuring down from what I'm just going to call the roof of space. All right, fantastic. Our plan now is to subtract those. Okay, but don't worry about them being negative. They're just negative because the reference point for the energies, the place where energy is 0, is if you could get all the way out to infinity, right? That's what that means. All the way infinitely far from the Earth. Or as I like to jokingly say, out where the aliens are. Okay, so using those little cartoon aliens as a guide, we're going to subtract. Right? It's kind of like we're talking to them, saying, hey, what do you think about this little satellite space probe thing we're launching? And the aliens would say, well, you finished this far below us, but you started that far below us, right? And that's why those negatives are there. And we're just going to look for difference, so we're going to subtract. There are a lot of negatives here, so you want to be careful. But if you are, you can come up with this great value for how much work it would be to lift that space probe up. 4.78 times 10 to the 8 joules. It's a lot. It's very, very expensive in an energy sense to get into space. And so that's great. We've been trusting this calculus formula to figure out exactly how much it will be to lift that thing up into space. But there's a problem. That's just the energy for the lift. And satellites have to actually be in orbit with some velocity. So in addition to lifting it, we're going to need even more energy. We're going to need some kinetic energy sideways to get that thing to stay in a nice, perhaps, circular orbit. So let's go and figure out what kind of velocity you would need to be in a circular orbit up at that height. Okay, well, we did this in the previous chapter. If you forget, you can always just go with this equation, F net equals ma, and you'd put in your force of gravity, and then mass times acceleration. And we found that, oh yeah, that turns into this v equals the square root of gm all over r. So I know the r, right? They're telling me we've got to be so far above the Earth. We've added on the Earth's radius. There's the r value for that. And then this will tell me exactly how much velocity I need. I'm going to reuse this number, so I'm just going to try to keep it nice and precise. 7,150.99 meters per second. If somebody asked me on a test, well, give me an answer, well, I put some units on the end and I trim it down to the appropriate number of sig figs. But if I'm going to reuse this number, maybe I'll use that precise one. Okay, great. Well, let's find out how much kinetic energy there is if you're going that fast. Right? Think back to grade 11. Kinetic energy was just 1/2 mv squared. So I would go 1/2, massive little space probe, and it's going that fast, and that's got to get squared. And when I tried that out, I had this number, 1.07 times 10 to the 9 joules. One of the reasons why I actually wrote down all of these digits here to try to be super precise is I just wanted to show you an interesting little pattern. This number, it's difficult to see this because the number is so big, right? It's in scientific notation, it's so large. But that number, if you take a look back, I'm just going to go back here. That number is exactly half as big as this number, minus the negative sign, right? Kinetic energy came out positive, but it is exactly half as big as this. You take that 2.15 and you cut it in half, and you would be looking at this number right here. That's no accident. That's going to happen every single time. It's probably worth a little note in there. Okay, so if you're next time doing this question and you're trying to figure out, well, how much kinetic energy is there? If you take a look at the potential energy in orbit, remove the minus sign and cut it in half, you're there. So I just made a little note, said, well, if you ignore that plus minus issue, because the kinetic energy is not negative, that kinetic energy number, the 1.07, is exactly half as big as the 2.15 number when it's in orbit. And you can trust that next time. So the total amount of work from your rocket, if you really want to lift that 42 kilograms up and put it into a nice circular orbit, is actually both the lift and the push, right, in order to give it a nice little bit of motion. So it's quite a bit of energy in order to get that space probe up into orbit and ready to go. Once you did have that space probe up into orbit and ready to go, you might be wondering, well, can I go farther? And the answer is sure, but let's stop here for just a moment, and before we take this thing maybe all the way out to forever, and let's find out how much energy we've got so far. Let's just do our usual thing we did in Physics 11, where we would find total amount of energy by adding up kinetic and potential. But now that we're doing this with orbits, it's kind of neat the way the numbers all fall into place with their plus and minus signs. This is your kinetic energy, it's positive, and it's the smaller of the two numbers. And then here's your potential energy, it's negative, and it's twice as big. So the negatives are going to win, right, because they're larger, but the amount that it wins by is exactly the same size as the small number. So this is what we call the total energy of that probe when it's in orbit. And space scientists, when they're doing their work, they really like to talk about how that total energy came out to be negative. In other words, you don't have enough energy right now to get all the way out to infinity. You can't get to, where we jokingly say where the aliens are, because you just don't have enough energy to get all the way up to zero. Zero is kind of the goal, and it's all the way infinitely far from the Earth. So if your total energy comes up negative, which this satellite does, and all satellites will if they're going around the Earth, then we would say, hey, it's stuck to us. It can't get away. Even if there was a big trampoline that it could bounce off of to try to redirect itself, it would not make its way infinitely far from the Earth. Well, what if you did want to go infinitely far from the Earth? This number actually tells you how much you're short, right? We're actually below getting all the way out to infinity by that amount. So let's take a look at this last little issue of escape velocity. This is what kind of speed you would need at the location you're at in order to just make it. So if you're coasting away from the Earth, you'd be traveling away from the Earth but slowing down because of gravity. And the goal is to just slow down to speed 0 when you're finally infinitely far from the Earth. And so the actual calculation would look something like this. There's the before picture, right? We're going to start at the Earth, some distance away, with some awesome velocity, and then try to just coast our way away from the Earth. When we're done, we want to be up on the roof of space. Okay, and I sort of say that jokingly, right? We want to be, as far as the calculus is concerned, infinitely far from the Earth, up on the roof, where the little cartoon aliens are. And it's okay to be stopped. We can have no kinetic energy if we can get to there. So we've got no kinetic energy, and if we're all the way up on the roof, up where the little cartoon aliens are, then we've got no potential energy either. So the conservation of energy story says, why don't you take your total energy? We actually already saw that number, right? For that satellite, it was negative 1.07. And you've got to get all the way to 0. So we need some more energy in there. We would need more speed in order to accomplish that. If we take this idea and just kind of rearrange it a little bit, we can come up with a formula for exactly what velocity you would need. Your kinetic energy plus that negative potential has to finally top out at 0. So in other words, the two sizes would have to be equal to each other. Now, they're not equal to each other in orbit. In orbit, this one is half as big. But if you could make this one actually equal to that one, then you could slide your way all the way out to infinity. Well, that could be tidied up quite a bit. We could cancel the little m's, maybe multiply by 2, and then take a square root. And so here's an equation, if you're interested, that will tell you what kind of speed you would need in order to make your way all the way out to infinity just by coasting. It's actually remarkably similar to the one we saw for orbits. That one was the square root of gm over r. This one has an extra 2 underneath the root sign, making the final answer root 2 times as big. Final little example of the day, we could figure out what kind of speed you would need from the moon's surface in order to leave and just get infinitely far from the moon. I think for fun, when they were on the moon, a little over 50 years ago, they took some golf clubs and a golf ball, and just for fun, they were kind of hitting a ball around. Can you imagine if you could hit the ball so fast, like driving it off a golf drive, that it actually left the moon and never came back? What kind of speed would you need? Well, this would allow us to calculate that. We could do that square root of 2, big G, one number for the whole universe, and then the mass of the moon divided by where you're first hitting that golf ball, which is the surface of the moon, 1 radius away. I just did this because I was curious to see, is there any way you could hit the golf ball that fast? Probably not. 2,000 meters per second, right? So basically 2.37 kilometers per second. If you could launch a golf ball that fast, then it would actually never come back. It would go up, 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 and slow down, but never quite come back, right? It would just get to infinity and then stop. And that's the end of one really big day of notes, taking a look at what happens when the force size is changing. And the gravity one is the big one, where we're using that equation, that negative g m all over r.